We've talked a lot about logarithmic and exponential functions and their properties, and then how to solve logarithmic and exponential equations. So now we're going to put it to use, and we're going to look at some word problems and some real life models. So we're going to start with some financial stuff. When we talk about simple interest is interest that's earned one time. And the formula for that is I equals P or T. So I is your interest. That's how much you're getting on it. And remember, this is going to be a one-time amount. P is your principal. Okay, that's your initial amount. How much did you invest initially? R is your interest rate. It always has to be expressed as a decimal. And then T is going to be time. So when we talk about money, your interest rate's usually a yearly interest rate, so your time would be in years also. But some of these concepts are we're gonna see in other examples where we could talk about the growth of bacteria. You want the rate and the time to be in the same unit. So if we're talking about bacteria growth per hour, then we would want the time to be in hours also. But for now, when we talk about money, interest rates usually in years, time's going to be in years also. So if we had simple interest, I equals P or T, it's principal times your rate times your time. That's how much interest we would get on an investment one time. To find that future amount, which is what A stands for, then we would take the principal, how much we invested, plus the interest rate. Compound interest happens when we are getting interest instead of just one time, multiple times. So we may do yearly or semi-annually. We may get interest daily or weekly or monthly or so on. So the formula is a little bit more interesting. Now we're talking about how many compounding periods we have, and that's what N stands for. And that's going to be the number of compounding periods per year. So if we say quarterly, then N would be 4. If we say daily, N would be 365, and so on. And then when we talk about continuous interest, now we're talking about interest that's being compounded essentially every second of every day. So let's look at a few examples. Number 7, we are investing $100 at 4% compounded quarterly after a period of 2 years. We want to know how much is going to be in there. So it's asking us to find that amount. So we are investing $100. Our interest rate is 4%. So as a decimal, that would be 0.04. It's compounded quarterly, so that would be 4 times a year. And we're going to leave it in there for 2 years. So if we want to know how much is going to be in there, your key word here is compounded in some way. So compounded quarterly means that we're going to use that compound interest point formula. It's that guy. Our principal is 100. Interest rate is 0.04. N is 4. Time is 2. Before you type this in the calculator, you're going to want to simplify that exponent. So that's going to be to the 8th. Make sure you put parentheses where I have them here. And just be careful how you type it in. When I typed it in, and since we're talking about money, I'm going to round to 2 decimal places, so the nearest cent. So I got 108.29. So that's how much would be in this particular account after 2 years. That is a one-time investment. So if we look at how much interest was earned, we would take that future amount And then we would subtract how much we started with. So in this case, we ended up with $108.29. We invested $100. So we put our money in this account for 2 years and we left it alone. We had $8.29 in interest that was added to this account. Now, let's change the scenario. In 13, we are investing $1,000 at 11%. This is compounded continuously. That's your key to let you know you're using that continuous formula. And we're going to leave it in there for 2 years as well. So our principal is $1,000. Our interest rate is 11%. And our time is going to be 2. We're using the PERT formula, A equals PE to the RT. P is 1,000. Our rate is 0.11. Our time is 2. Make sure you simplify that exponent. I think it makes it easier to type it in. So in this case, we had 1246.08. So there's our amount. So in those two problems, we were trying to figure out how much would we have at the end of some time period. The next few problems are a little different because now we're asking how much do we need to put in. We're looking for the principal if we want to get a specific amount. So let's look at 15. We want to get $100 after 2 years, and we're looking at 6% compounded monthly. So that tells us which formula we're using. So I'm going to flip over to the next page. Let's talk about the information we have. We want to get 100, so that's our A. We're leaving it in there for 2 years. Interest rate is 6%. And it's going to be compounded monthly. Monthly means 12 times a year. If it's compounded monthly, we're using that compound interest formula. So let's substitute in everything we know. So we know R is 6%, 0.06 is a decimal, N is 12. Our future amount is 100. We are looking for P here. How much needs to be invested? Before we do anything, I'm going to simplify that exponent. 0.06 divided by 2, 0.06 times 2 is 0.12. So this guy's just a number. It's not a very nice number. So I'm not going to plug it in the calculator right now. But it's going to be a number. Now we want to get P by itself. Right now P is multiplied by that number. So the opposite would be to divide by that number. And we could simplify the 0.06 divided by 2 too. But I'm going to leave it. 0.06 divided by 12, I mean. So now that's going to cancel with that. We have P by itself. And it's going to be 100 divided by 1 plus 0.06 divided by 12 to the 0.12. Okay, now why would I want to do that instead of type that into the calculator? If I type it in too early, if I round to just 1 or 2 decimal places, it will throw that final answer off. So your best bet is to leave this as an exact form and then type it in at the very end. So now we're going to type this in. Be careful how you type it in. Watch your parentheses. You can type it in just as you have it there. And then you'll get your P. So we're going to have to invest Hold on just a minute. I think we made an error somewhere. We left off our time. We had a 2 here. Alright, let's look at this. A equals P times 1 plus R over N to the NT. My writing was really messy just a minute ago, and that's what threw everything off. So let's rewrite this. This is an NT. P is what we're looking for. Our interest rate is 0.06. N is 12. T is 2. So before, my writing was messy and I thought that was an R. So let's try this again. I'm going to simplify that exponent. That's going to be a 24. And now remember, this guy's just a number. So we're going to divide by that number. So that's going to allow us to get P by itself. So here's our exact value. Be careful when you type it in. If I round to the nearest cent, I got 88.72. So what that means is we would need to invest $88.72 now so that we would have $100 in this account after 2 years. Okay, let's look at 22. Same kind of thing. We want to get $800 after 2.5 years at 8%. We're compounding continuously now, so we're using a different formula, but the process is still the same. So we want to get 800. That's our future amount. Our time is in 2.5 years. So we're going to write that as a decimal. Interest rate is 8%. We're looking for principal. And we're compounding continuously. So there's our formula. Let's substitute in everything we know. 800 equals PE to the R times T. So I'm going to simplify that exponent. 0.08 times 2.5 is 0.2. To get P by itself, we're going to divide by E to the 0.2. Now, that's not going to be a very nice number, but once again, we're going to keep that exact value so that when we type that final answer in, we're going to be accurate up to 2 decimal places. We would actually be accurate to as many decimal places as we want if we use that exact. But since we're talking about money, we need 2 decimal places. So we need $654.98 to invest now so that we would have $800 in 2.5 years. Now, let's take a look at the next one, number 42. Now we're looking for time. How many years will it take for an initial investment of $25,000 to grow to $80,000? We're going to have an interest rate of 7%, and we're going to be compounded continuously. So let's talk about this one. This is number 42. So we want to start with $25,000. And we want to grow, that's our future amount, to $80,000. Our interest rate is 7%. We are looking for time. And it tells us that we're going to be compounded continuously. So we are using that formula. Now, let's substitute in everything we know. So now we have an exponential equation we want to solve. And remember, we're going to have to isolate that E term. And our final goal is to get T by itself. So let's start by dividing both sides by 25,000. So if we do, we're going to have E to the 0.07t on the right. 80,000 divided by 25,000. is going to be 3.2. This is a nice decimal, so I'm going to leave the decimal. Now we can take the ln of both sides. And the ln of e is going to cancel, so we have 0.07t. The ln of 3.2 is not a very nice number, so I'm just going to leave the exact value. So to get t by itself, we're going to divide by that 0.07. So there's our exact answer. Now, if we're talking about banking, we're going to want, and time, we're going to want a decimal approximation. So when you type this in, make sure you put parentheses around that ln. That's the only number you're taking the ln of, and then you're dividing that whole thing by 0.07. So it looks like it's going to take 16.62 years for this investment to grow. Let's look at one more example when we're talking about money, and this is going to look at doubling time. So we want to know, how long is it going to take for an investment to double if it's compounded continuously at a rate of 6%? So let's think about what we know. We know we're using that A equals PE to the RT, the PERT formula. We know that we have an interest rate of 6%. We also know we're looking for time. So we don't know how much we're starting with. And it doesn't matter how much we're starting with because the time's going to be the same. But we know we want to double it. So let's say that principal amount, let's just be very generic. Let's call it P. We could use $1 here, or we could use $100. But I'm going to be generic because I want to show you what's going to happen with the variables. So if we're starting with an amount P, then if we double that, then we're going to have 2 times P. So let's take all of this information and let's substitute it into this formula. So if we do that, we're going to have 2P is equal to PE to the 0.06T. Goal, remember, is to get T by itself, so we're going to divide by that P value. So we're going to get 2 here. And now we're going to take the ln of both sides. On the right, we're going to have 0.06t. And then if we divide by 0.06, then t is going to be the ln of 2 divided by 0.06. Which would be about 11.55 years. So that's how long it would take us to double. So what I want to show you is that suppose we would have chosen an amount. It really doesn't matter how you approach this. Let's say we wanted to invest, I don't know, $100. Then if we were to double that, and the reason we're doubling, remember, is because they're asking us how long it takes to double. Then double 100 would be $200. Look at what happens when we substitute this in. So that's your first step. Divide everything by 100. So we're going to have 2 is equal to e to the 0.06t. Now look, we are right back at this step, so everything works the same way from here. So it truly doesn't matter whether you go very generic or whether you go very specific. And it doesn't even matter what number you pick here as long as you double it here. You're always going to get the same answer. Divide by 0.06. That exact value is going to be the same on both of those. So that's a fun problem. So now let's talk about growth and decay. So when we talk about growth, we could talk about things like bacteria cultures. We could talk about colonies of mosquitoes or colonies of other types of bugs. Colonies of anything, really. Population growth in the beginning can be modeled by an exponential growth type problem. Even when we talk about the coronavirus, in the beginning, that was a very exponential growth that we had when we were talking about the number of people who were infected with that. And then it starts to level off at some point, which becomes a different type of graph, called a logistic graph. So exponential growth follows, it's called the law of uninhibited growth. And your formula really looks a lot like that PERT formula. And that's because it is the PERT formula. They're using a different variable here instead of P. Okay, so you're always going to be growing if that rate, which we used R when we were talking about money, now we're using K. So if that rate is positive, you're going to be growing. That's why when we talked about money problems, we always had more in our account because our interest rate was always positive. You're going to be decaying, so you're going to be losing amounts if our K value ends up being a negative number. Okay, so that usually happens when we talk about radioactive decay. So let's look at a few examples. Let's look at number 5. We have the growth of a colony of mosquitoes. The population of the colony of mosquitoes obeys the law of uninhibited growth. So that tells us it's going to follow this model. Now, A says if N is the population of the colony and T is the time, express N as a function of T. So instead of using A's, they want to use N's in this problem. So N of T, or we could just say N, is equal to that initial value, e to the KT. Now B's given us some information. It says there are 100 mosquitoes initially, and there are 1,800 after day 1. We want to know what's the colony size after 3 days. So that N sum naught, that's your initial amount. And in this case, that initial amount is 1,000 mosquitoes. So our model initially is going to look like this. So that's using that first piece of information. Now they're telling us after a day, there are 1,800 mosquitoes. So we now have a future amount. That's our N. We don't know the growth rate, but we know after 1 day we had 1,800. That gives us enough information to solve for that K value. So let's divide both sides by 1,000. This is a nice decimal. I'm going to use that decimal, 1.8. That's going to be equal to e to the K. We're looking for that growth rate. So let's take the ln of both sides. So the ln of 1.8 is equal to our K value. So there's our growth rate. And if we were to type that in the calculator, we would get a positive number. That's how we know it's going to be growing. Now they're asking us, what's the size of the colony after 3 days? So here's what we know. We know the growth rate now. So let's substitute it in. We started out with 1,000 mosquitoes. So there's our model. Now we want to know how many are we going to have after 3 days. So let's substitute 3 in. That's going in for that time. Be careful when you type this in. This is 3 times the ln of 1.8. So we have 1,000. This is E to the, and use your parentheses here. It's the ln of 1.8. Close that ln and then multiply by 3. All of that is in the exponent. So when I did this, I got 5832. So we would have 5,832 mosquitoes. That's a lot of mosquitoes. Now let's look at C. They're asking how long. So we're looking for time here. How long until we have 1,000 mosquitoes? So we're going to use this model. And that 10,000 is going in for N. Our first step is to divide both sides by 1,000. That's going to give us a 10. Now let's take the ln of both sides. So this ln and this e will reduce. This e does not reduce with this ln because it's multiplied by t. You would have to rewrite that, so be careful on these when you're doing these. But this ln and this e reduces, so we're left with just everything in that exponent, which is the ln of 1.8 times t. The ln of 1.8 is just a number. To get t by itself, we're going to divide both sides by that number. So we have the ln of 10 divided by the ln of 1.8. So it looks like it's going to take about 3.92 days before we have 10,000 mosquitoes. Let's look at another one. Let's look at number 6. So we have a bacteria culture that obeys the law of uninhibited growth. A is asking if N is going to be the number of bacteria of the culture and T is the time in hours. We're going to express N as the function of T. So that A is going to be really similar to what we did before. They're just using A's here instead of, they're using N's here instead of the A's. So we're going to end up using that formula. Now B is giving us more information. We have 500 bacteria that are initially present. There's 800 after an hour. We want to know how many is going to be present in 5 hours. So let's look at this one on the next page. We know there are 500 initially. So we're using that formula. Now we also know there's going to be 800 in an hour. So 800 is our N. That's our future amount. And that's in 1 hour. This gives us enough information to find K. You're always going to have to find K first before you can solve the second part of the problem. So we're going to divide everything by that 500. 800 divided by 500 is 8 over 5. And 8 divided by 5 is a nice number. I'm going to go ahead and use that decimal, which is 1.6. So now let's take the ln of both sides. So we have the ln of 1.6 is equal to K. So there's our growth rate. That's going to be a positive number. That's how we know it's growing. So here's our formula. The ln of 1.6 is a number, and that's multiplied by T. Now, I said I turned this into a decimal because it's a nice number. If this were not a nice number, and by nice I mean something that terminates within a reasonable number of decimal places, then I would keep that fraction, just to keep that exact value. So the second part of part B asked how many is going to be present after 5 hours. So we need to find N of 5. Be careful, all of this is in the exponent. And I got 5242. And that rounds to 5243. So I would say about 5,243 bacteria would be present in 5 hours. So C is asking how long before you have 20,000 bacteria. So we're going to set 20,000 equal to our equation. That's our N. Divide both sides by 500. And that's going to give us a 40. Take the ln of both sides. And when I take the ln of this side, I'm left with just that exponent. Divide both sides by the ln of 1.6. So there's our exact value. And that is approximately 7.85. And this would be an hour, since all of our time's in hours. Okay, let's look at number 9. In 9, we're talking about half-life. So the half-life of radium is 1,690 years. If we have 10 grams now, how much are we going to have in 50 years? So the difference between this one and the other ones is that now we're decaying. So our K is going to end up being a negative number. So we know the half-life is 1,690 years. So here's what we know so far. We're starting with 10 grams. Now, let's use that half-life information. We know that in 1,690 years, so there's our time, we're going to have half of this amount. Well, half of 10 is 5. That gives us enough information to figure out what K is going to be. We can divide both sides by 10. 5 divided by 10 is 1/2. Nice decimal, I'm going to use the 0.5. We can take the ln of both sides. The ln of e to the 1690k is just going to be that exponent. And then we're going to divide both sides by that 1690. So here's our formula. We started out with 10 grams. Our decay rate is the ln of 0.5 divided by 1690. That's not a very nice number. I'm going to leave that exact number. If you round these, I would use 6 to 8 decimal places, maybe even more. Okay, we know this is going to be negative because when we take the ln of a fraction between 0 and 1, we're always going to get a negative number. So now they're asking how much is going to be present in 50 years. So we need to find A of 50. So all of this is in the exponent. So I got the amount to be about 9.797 grams. So not much is decayed in 50 years, which makes sense because the half-life is over 1,600 years. Let's look at that last problem. We have a fossilized leaf that contains 70% of its normal amount of carbon-14. We want to know how old the fossil is going to be, and we're going to use 5,700 years as a half-life. So let's look at this one. This is number 12. We know we're using this formula. So we know the half-life is 5,700. So let's say we started with 1 gram. So then how much do we have now? Well, if we have 70% of 1 gram, then that would be 0.7 grams. So you can start with some kind of a generic initial amount. You could use an A if, like we did in the money problems, or you can use, some arbitrary amount here like 1 or 10 or 100. But we know we're going to have 70% of that original amount right now. So that's how much we have now. We want to know how old it is. So we're looking for the time that's related to how much is left in that now. So we've got to figure out first what K is. What is that decay rate? So let's substitute in what we know. We know that if we start with 1 gram, then after 5,700 years, we're going to have half a gram left. Okay, and like we said, it doesn't matter how much we start with here. We could use 1, we could use A. Setup's going to be pretty much the same. So if we simplify this, we're going to have 1/2 is equal to e to the 5,700k. Let's take the ln of both sides. ln of 1/2 is the ln of 0.5. The ln of this e term would just be that exponent. So our k value is the ln of 0.5 divided by 5,700. So there's our decay rate. So here's what we have. We said in the beginning we had 1 gram. I'm going to use a 1 there. We could use a generic amount or any amount. Our decay rate is the ln of 0.5 divided by 5,700. And then t. Now, we are looking at 70% of this amount left. So that's going to be a 0.7. Clean it up. 1 times anything is going to be just that anything. Now we can take the ln of both sides. To get t by itself, we need to move this guy. So we can divide. So I'm going to rewrite that. So isn't that the same thing as this? And then if we do keep, change, flip, that will tell us what t is going to be. So we have the ln of 0.7 times 5,700 divided by the ln of 0.5. So this thing is approximately 2,933 years old.